Welcome to lectures on instrumentation in process industries. We are discussing the working and layout and instrumentation measurement in petrochemical plant. So in the previous class we have discussed the layout of petrochemical plant and we have taken each block and we have explained the process based on that layout. And we have listed down 10 important petrochemicals and their applications. And we have defined various important processes, that is thermal cracking, catalytic cracking, polymerization, and alkalization and isomerization. So the thermal cracking is the important process in the petrochemical in which the heavy molecules, hydrocarbons, are divided into smaller ones and they are collected in different levels of temperature and pressure conditions so that we'll get different kinds of petrochemicals after thermal cracking. And similarly, fluid catalytic cracking. In this also, the catalyst chemical element will help us in the process of cracking, so that the finally we have different petrochemicals at the output of fluid catalytic cracking. So in this class, we'll discuss fluid catalytic cracking, how it is done, and byproducts of crude oil, and working of distillation column, and a PI diagram of distillation column we'll see. And after that, measurement and instrumentation part we discuss, that is the measurement of flow, pressure involved in petrochemical plant, and measurement of density of those fluids, and working of centrifugal pump, because that is the centrifugal pump or petrochemical pump which is widely used in the industry, that we will discuss, and what are the safety measures we have to take care of so that it should not be hazardous to human beings, working personnels in the industry. So those of safety measures we consider today. Now, so this is the petrochemical plant we have discussed yesterday. In this various, so after refining, this is the petrochemical plant we have discussed. So this petrochemical plant, here is a steam cracking section and dehydrogenation process. So these are the cracking techniques used, and the feedstocks used are, these are the feedstocks to the petrochemical plant, that is the naphtha, and mostly naphtha, it is the 60 to 70% of naphtha is taken. And we have discussed these petrochemicals, here ethane and its derivatives, and propylene and aromatic fractions, and C4 C5 fractions. So these are the petrochemicals and how they are used in various so this is the oil and natural refinery section. So the first part of this is, these are the feedstocks So these are the feed stacks for the petrochemical plant. So here mainly the naphtha plays important role. These are the two elements that are widely applied to petrochemical plant, and others widely used in daily life in the transportation. So this is the actual refinery section, oil and natural gas system. In the world, most of the plants are this. That is 95% of the plants are this, and only 5% of the plants are petrochemical plants. So because such applications and because that crude oil is naturally available, it is the plenty of element that is naturally available and which is processed in the refinery, oil and natural gas refinery industries. So these industries plays important role, and it is widely spread over 95% industries spread over these types of industries. Only 5% are petrochemical plants. Here, in this class, we concentrate on fluid catalytic cracking. So, this today, FCC is the most popular of the catalytic cracking processes, and FCC units consist of three primary pieces of equipment. That is the reactor chamber in which the hot feed is mixed with the catalyst and the cracking reactions take place. So that is the main chamber in which the catalyst is added so that the mixture gets reactions, cracking take place. And the next one is the regenerator in which the catalyst is regenerated by burning the coke produced in the reactor from its surface. So this that means the catalyst once again it is regenerated in this section so that it can be reused in the reaction chamber. And the next one is the fractionator where the cracked hydrocarbons are separated into useful products. So this is the fractionator distillation column. So this will because from top to bottom it will be in different pressure and temperature conditions, and at different levels it is tapped so that different products are separated and can be derived. So the most FCC units can be described as being one of three general designs. That is a stacked design, a side by side design, or a riser reactor design. These are the three general designs widely used. The terms stacked and side by side refer to the relationship of the reactor to the generator. That means how the reactor and generator, both how they are placed physically, and how the that is catalyst is input into the reactor. Based on that, these two are designed. In the riser and reactor design, there is no reactor vessel in the conventional sense. The cracking reaction takes place in a riser pipe which connects the regenerated catalyst storage area and the catalyst separation equipment. So that is the separate design, riser and reactor design. So physically we can't locate the reaction chamber, but the reaction pipe which is connected to the catalytic storage area, that is separate, so that catalytic cracking will take place in that, and the catalyst is continuously available to the rise and reactor design. So in this we will consider the side by side design FCC. So in this, the design consists of a reactor vessel built alongside of a catalyst regenerator with long radius U bend piping connecting the two vessels, that is the reactor chamber and the catalytic regenerator chambers. Both are connected with a U bend piping connection. So the process is based on a continuous circulation of the catalyst between the reactor and the generator. The generated catalyst flows from the generator standpipe into the bottom of the reactor through a long radius U pipe. So that is the physical arrangement then done. So whatever the catalyst, that catalyst is continuously being pumped through bottom, so that the reaction takes place, so that fast catalytic cracking will take place. So this is the design here. We have the reactor you can observe here, and the regenerator you can observe here. You see the reactor and regenerator. Observe here a U pipe, U shaped pipe. Here, this is the U shaped pipe here, which is connecting the regenerator and reactor. So, if you observe here, the reactor, FCC reactor, is taking the steam, and the different reaction here takes place within the. Now you see the reactor, it is taking the steam, and olefin feed is there to the reactor. You see the reaction takes place in this at a different temperature and pressure conditions, and after that the fluid is passed into the fractionator. So this fractionator, it is the distillation column, fractional distillation column, in which the three products are available like this. These are the products available from the fractionator, and from the top it is sent to the the condenser. So this condenser will produce as gasoline. So next, here light cracked gas oil is available here, and heavy cracked gas oil is available here, and this cycle oil is fed as a olefin feed into the reactor once again. These are the steams. So now the fresh catalyst is already being circulated into the feed into the reactor chamber, and here from the bottom the spent catalyst is taken, and with the help of main air reaction in the regenerator. So the regenerator will once again take this spent catalyst and reform it, and it will pump it into the reactor once again. So this is the catalytic flow direction, like this continuously it will flow like this. And you see, from the top of this, flue gases are utilized by the boiler section. So this is the arrangement, fluid catalytic cracking sections. So the hydrocarbon feed is introduced into the catalyst flow in this U pipe. So that is the hydrocarbon feed. Generally, here, that is the through U pipe that we have seen just now, and the heat causes the feed to expand or vaporize and fluidize the catalyst. The catalyst and hydrocarbon feed then enter the reactor, that is the olefin feed here in this case. Olefin feed and catalytic element both are fed into the reactor where the cracking reactions are completed. In practice, most of the cracking of hydrocarbons is accomplished in the U pipe prior to entering the reactor. That means, you see, through the pipe, U pipe, both are pumped into the reactor, that is the catalyst and olefin. So most of the reaction takes place in the pipe itself, and finally in the reactor the final reaction will take place. So now let us see the byproducts of crude oil. So oil and natural gas industry produces these byproducts: LPG, petrol, kerosene, diesel, aviation fuel, mineral oil, paraffin wax, bitumen, tar. So these are the byproducts of crude oil. Now, so these are the products. So here for the domestic purpose, LPG gas, and for LPG vehicles also available, and for the petrol in transportation vehicles use, and kerosene is used in domestic purpose, and diesel also for transporting vehicles, and aviation fuel for the flights aviation purpose, and mineral oil is used for a household purpose, domestic purpose, and paraffin wax, and this is used in commercial purposes. Tar is used in roads and construction purpose. So these are the important uses of this. Now you can remember here, instead of that list, you can see the actual oil and natural gas industry. It is operating like this. This is the distillation column. You see the crude oil here. The oil is heated in the furnace, so that crude oil is pumped into the, after heating, it is pumped into the distillation column. If you observe here, the distillation column is having different sections. You see, from the top at 20 degrees centigrade, the fluid available at the tap is butane and propane, which are used as feedstocks to the petrochemical plant. And next, at 150 degrees centigrade, petrol is collected. And next, at 200 degrees centigrade, kerosene is available. At 300 degrees centigrade, diesel is collected. At 370 degrees centigrade, fuel oil is taken. So at 400 degrees centigrade, lubricating oils and paraffin wax, asphalt, these are the products available. You see, this is the, you see, single crude oil, how with the help of distillation column, by maintaining different temperature and pressure along the distillation column, how different products are produced, you can observe. So a typical distillation contains several major components. A vertical shell where the separation of liquid components is carried out. So the column internals such as trays, plates and or packings which are used to enhance component separations. Observe here, already we have seen these are the different compartments, trays. You see, trays here to separate different products like this. So these trays and plates are used to separate different byproducts. A reboiler to provide the necessary vaporization for the distillation process. So a condenser to cool and condense the vapor leaving the top of the column. Condenser also will be provided. A reflux drum to hold the condensed vapor from the top of the column so that liquid can be recycled back to the column. So that is the reflux drum to hold the condensate reflux item so that it can be recycled into the distillation column. Observe here. So you see this is the overall construction and structure of distillation column. You see the oil is fed here into the into the distillation column. So this is the crude oil that is fed into the distillation column. Observe here, a from the top of the distillation column, a product is separated and collected here, and at the same time this top vapor, this is the top vapor, so this top vapor is directed towards the condenser, so which will condensate the vapor into fluid, and that fluid is collected in the reflux drum. So this is a converter, that means it will convert, this condenser will convert vapor into fluid. That fluid is collected in the reflux drum. This is the reflux drum. So this from the reflux drum, this fluid once again pumped into the reactor, that is the distillation column. So this is the arrangement, and in the bottom we have reboiler here, where the product is collected here at the bottom, and that is collected like this, and sometimes what happens, some portion of this is reboiled here and repumped into the distillation column like this. So this is the way how distillation column works. For a single fluid flow path, we have taken example. This is the single flow path, another single flow path. But such arrangements are available at many sections at different temperatures of the distillation column. The liquid mixture that is to be processed is known as the feed, and this is introduced usually somewhere near the middle of the column to a tray known as the feed tray. So the feed tray divides the column into a top section and a bottom section. So the top section is the enriching or rectification section. The bottom section is the stripping section. The feed flows down the column where it is collected at the bottom in the reboiler. So the feed flows down. As it flows down, it is separated into different fluids, products, and finally at the bottom, one product is collected and it is reboiled and once again feed into the distillation column. And from the top, vapor it will be collected by the condenser and it is converted into the fluid and reflux into the distillation column. Heat is supplied to the reboiler to generate vapor. So that is the heat purpose, and the source of heat input can be any suitable fluid. Although in most chemical plants this is normally steam. So the steam will gives the heat, it will be used as a heat input in the reboiler. In refineries, the heating source may be the output streams of other columns. That means the output columns, that is where in which the byproducts are running. So those columns can be used as heating sources, and the vapor raised in the reboiler is reintroduced into the unit at the bottom of the column. The liquid removed from the reboiler is known as the bottoms product or simply bottoms. You see, these are the bottoms. That means the products are named as bottoms. And observe here the feed fluid which is input into the distillation column, it is flowing down, and the vapors because here the furnace, that is heat input, is there, and the vapors are produced, and those vapor are moving upwards the distillation column. Hence, at different tap locations of each tray, each byproduct is collected like this. And in the bottom section, we have, so here the at the bottom reboiler is there, and heat is supplied to the reboiler to generate vapor, and the source of heat can be any suitable fluid, although in most chemical plants this is steam. In refineries, the heating source may be output streams of other columns. The vapor raised in the reboiler is reintroduced into the unit at the bottom of the column. So the liquid removed from the reboiler is known as the bottom product, or simply bottoms. So this is the reboiler section. You see how the fluid is used here to heat the reboiler, and the feeding crude oil, now it is descending from top to bottom in the blue lines. So this is collected at different tap locations, and the vapor is moving upward. So the vapor moves up the column, and as it exits the top of the unit, it is cooled by the condenser. So the condensed liquid is stored in a holding vessel known as the reflux drum. Some of this liquid is recycled back to the top of the column, and this is called the reflux. The condensed liquid that is removed from the system is known as the distillate or top product. Now let us see that unit here. So this is, you see, this is the top section. The vapor is moving on the top to the condenser, and the condenser converts this vapor into the fluid, and that fluid is pumped as a reflux into the distillation column once again, like this. So the vapor is moving like this to the condenser, then it is converted to the fluid and collected in the reflux drum, collection drum. So this pump will pump the same collected fluid into the distillation column, and some of the product is tapped and collected as a product. So that is the distillate product. Now if you observe here, this is the refinery section here. Oil and natural gas, you see the atmospheric distillation column. You see the first the crude oil is sent to the furnace. Here the crude oil is heated up to the 750 degree Fahrenheit, and in middle it is pumped into the distillation column. So now this fluid is moving down like this, crude oil, and once it is descending from this middle section to the bottom, because this is a distillation column, and here throughout the section you find a different pressure and temperature values. Here, as you come down, the temperature increases. So 300 degree Fahrenheit, 390 degree, 570, 840, 910 degree Fahrenheit. And if you at 300 degree Fahrenheit, you will collect naphtha. And at 390 kerosene is available. At 570 gas oils, diesel fuel is available. 840 lubricants are available, and 910 fuel oil is available. And at the bottom, asphalt, road tar at 1070 degree Fahrenheit, it is collected. So you see here different trays are there. Here trays. These are all trays. You see, and the vapors, lightweight vapors moves up. The fluid is comes down, and vapors are moving up. That is the thing. And these vapors at 70 degree Fahrenheit, you will have a tap section, which is this is the naphtha. This is the naphtha here. This naphtha is the product, output product from the oil and natural gas industry. So this naphtha is used as a prime essential feed stock to the petrochemical plant. And heavy fluid content is moving down, unrefined oil moves down, and gases are moving up. So now let us see the PID diagram for the petrochemical plant. Here one distillation column is taken here, and you see the PID, the symbols, pumps symbol, heater symbol, and flow control, transmit, flow transmit control, temperature transmit control. These symbols are standard symbols. How to draw process instrumentation diagram, piping and instrumentation diagram, you might have to learned that in the process control subject. In the process control subject, already the PID, drawing PID for different processes you have learned, and recollect them, and apply those symbols here to draw the PID structure of petrochemical plant. Here, if you observe, pumps, heaters, condensers, and equipment, that means controller and transmitter equipments here available. So for each loop, how a parameter is controlled here, it can be observed. So for example, let me tell you that, for example, this is a heater, Observe here, this is a heater, and to the heater there is a heating fluid that is pumped into the heater. So this heater temperature is to be measured by the temperature transmitter, and temperature controller is also here. It is fixed at the field level only, and current to pressure transmitter. So current to pressure transmitter. So then this pneumatic signal is applied to the control valve here, so that the heating steam that is flowing into the heater is regulated like this. And at the same time, the crude oil that is pumped into the distillation column at the middle section, so this is not directly pumped, but it is pumped through heater. So this fluid rate of flow can be regulated like this. You see, the orifice symbol is there here. So here, flow transmitter measures the flow of this crude oil into the heater section, and that flow rate is measured, and it is transmitted to the flow controller. And the flow controller, according to the set point, it will regulate the flow of this, and issues control signal to the control valve here. So before that, the electrical signal is converted to pneumatic signal with current to pressure converter. This is I by P. It is the current to pressure converter. So these things you have learnt in process control, and what you have to do is you have to get the symbols of mm, each chamber, each pump of the oil and natural gas or petrochemical plant. Similarly, if you observe here, you see the different tap locations here, pumps, and you have the here condenser here, and you have here the pump, and this is the heater. Once again it is collected into this, and you see the downstream, it is the reboiler. This is the reboiler section, that is the symbol of the reboiler. And so this is the way you have to analyze this P and I diagram of petrochemical plant. And what are the physical parameters to be measured in PCB? Because it is our instrumentation part. So here, as an instrumentation engineer, you have to know the different parameters that are to be measured in petrochemical plant. So the physical parameters are temperature, flow, pressure, density, viscosity, liquid level, velocity, composition, weight of the fluids. So these are the parameters we have to measure. For example, we have seen that flow rate, how the crude oil flow into the distillation column, it is regulated with the flow loop we have seen. Similarly, for the temperature loop, it will regulate the temperature of a vessel. So these are the parameters we have to consider, and these physical parameters, first they must be converted into electrical parameters so that they can be measured and controlled with the help of electronic devices. So for that, transducers are generally used. The transducers converts the physical variable into the electrical parameter so that the electrical signal can be processed with the control system, electronic control system, and after processing, it will regulate the parameter according to the set point value. So, with this, we will conclude our lesson that today we have discussed uh, thermal cracking and fluid catalytic cracking in this lesson, and we have discussed the byproducts of crude oil from the natural and oil industry. And after that, we have discussed the working of distillation column, and we have discussed the PI diagram of distillation column, and we have seen the important physical parameters that are to be measured and controlled in the petrol and petrochemical plant. So, with this, we can conclude here, and in the next class we will discuss measurement of flow density and measurement of temperature. These parameters we will discuss, and after that we will discuss the centrifugal forms that are used in petrochemical plant and handling of petrochemicals. The safety measures also we discuss in the next class. So with this we conclude our lesson. Thank you.